Okay, good morning. So we will continue our class on counters. So in the last class we have discussed asynchronous counters, how we can design an up counter and a down counter. Okay, so I have a recap of what we have discussed and or something like a summary. It is an interesting fact that you can see what are the various ways of connecting our clock two different flip-flops that we have seen in the previous class. So we can connect from the flip-flop either Q input you can connect to the clock or you can connect Q bar input to the clock. And we have seen the difference between these two. One will go for up counting and another will go for down counting if you are changing the Q and Q bar output to the clock. And similarly, one more thing is that if you are giving the triggering levels, if it is a positive edge triggering, then it will behave like something. If it is a negative edge triggering, it will behave like some other thing. So these differences I have summarized in a table, and from this you can really understand how this counting will happen in various cases. Okay, so let us see what happens. And here we are considering only edge triggering, right? So what edge triggering is? Edge triggering is whenever there is a transition from 0 to 1 or from 1 to 0, the corresponding output will get toggled. Here we are assuming that we are using a T flip-flop or a JK flip-flop with 1-1 condition. Okay. So assume that is a positive edge triggering. And if it is a positive edge triggering and if you are taking clock from Q, then it will, and if your output also you can take from either from Q or from Q bar, right? So if you are taking output from Q, it will be a double counter, and if you are taking from Q bar, automatically it will be up counted. Okay, because this will be Q and Q bar are complementary, so if it is down counting, automatically the other one will be up counting. Then next is if the positive edge triggering you are taking and the clock is given from the Q bar input, then the if you are taking from output from Q, then that will be up counter. So this one we have designed, this one we have done. And next one is we are giving a negative edge triggered clock, negative edge triggered flip flop we are using, and clock is given from the Q output of the previous state, so that will also be an up counter. So automatically Q bar will be down counter. And if the negative edge triggered flip flop I am using and the clock is from Q bar, so it will be a down counting. So it means that if you are having two flip-flops, the four various cases can happen. That is, this is Q, this is Q bar, this is Q and this is Q bar of the next input. So first case is I am taking positive edge triggering. So positive edge triggering, there is no bubble, here you can see no bubble, and Q is connected to this. This is the first case. Then what is the second case? Second case is again I am using positive edge triggering and instead of this Q I am connecting from Q bar. So this is a up counter. Then third case is I am using negative edge triggering. Negative edge triggering and clock is connected from Q input. So this is also up counting. Then fourth cases I am using negative edge triggering and clock is connected from Q bar output. So that is down counting. Okay, so here I am assuming that I am taking out from Q. So if it is from Q bar, then you will get the complement. If it is down, then there will be up counting. If it is up counting, it will be down counting. Like that. So that's the difference between. And for better understanding or for memorizing this concept, I will tell you one trick. Okay, see here, this is positive. This is positive. Q is also you can take it as, it is not complement, so you can take it as positive. So if both are positive, then if you are taking output from Q, it will be down counting. Here it is positive edge we are giving, and here it is complement. So you take it as negative. So if one is positive and the another one is negative, automatically if you are taking output from Q, it will be up counting. Then here it is negative, here it is positive. Both are different, right? One is positive and the other one is negative. One is negative and another one is positive. So in this case also you are getting an up counter when you are taking output from Q. Then if it is, this is negative and this is also negative, both the signs are same. If both the signs are same, then you will get a down counter. This is the case when you are taking output from Q. If it is from Q bar, this is just the reverse of that you will get. So this is an easy way to design. When you are designing, we just check this condition. If you are asked to design an up counter with a negative edge triggered flip-flop, what you have to do? Design an up counter with a negative edge triggered. Negative edge triggered up counter. So we have to take from output from Q and you can connect. Okay, if you are asked to do a negative using design a negative edge triggered counter, you have to design a down counter with a negative edge triggered flip flop. What you can do? You connect a negative edge triggered flip flop and the Q bar should be connected as a clock of the next input. Okay, so this is a summary of what we have discussed so far, and now we will be moving to a next part of this presentation, that is how we can go counting up to a particular level. So till now we have counted up to, if you are using n bit, I have counted up to 2 power n minus 1. Suppose you want to count below that. Suppose I am taking a 4 bit counter. So in that 4 bit counter I can count up to 2 power 4 minus 1, that is I can count up to 50. Suppose I want to design a counter that counts up to 9 only. What I can do? I need 4 counters anyway, because 3 counters you can count only up to 7. So if you want to count up to 9, what you can do? You have to use 4 counters. But in that case, after 9, again I have to go back to 0. Right? So how it is possible to design such a counter that can count up to a particular level, not up to the last bit pattern. I want to stop the counting in between. So what we can do in that case? So that we are going to see next. Okay. So now we are going to design a counter which counts up to 12. Okay, so in order to count up to 12, if you are having 3, if you are designing a 3-bit counter, you can count from 0 to 7 only, right? That is 2 power 3 minus 1, only up to 7 you can count. Then if you are using a 4-bit counter, you can count up to 0 to 15. Okay, that is 2 raised to 4 minus 1. 0 to 15 you can count. Okay, you know how to design that also. You have to use 4 different flip-flops. Then output of one flip-flop should be connected as a clock of the next flip-flop. So automatically it will count up to 50. And suddenly it reaches 15, it will go back to 0. That you know how to design. Now, actually in case of this particular design, I want to count only up to 12. So if it is 0 to 15, we say it as a mod 16 counter. Mod 16 counter means it will count up to 50. That is what mod 16 counter is. Here I want to design a mod 13 counter. What is the mod 13 counter? It will count from 0 to 12 and suddenly it reaches 12, it has to go back to 0. Okay, that is what mod 13 counter is. So it has to count from 0 to 12. So how we can design such a counter? Okay, so anyway we know we have to use 4 flip-flops for designing it. Because with 3 flip-flops we can count only up to 7. So anyway we need 4 flip-flops. So what we are going to decide is, we are having 4 flip-flops. And 4 flip-flops we are having. So normally what we are doing? We are connecting this to here. This is active low. and this output I am connecting here. So this output I am connecting here. So all are active low. So this is our Q0, this is Q1, this is Q2, and from here I get Q3. Okay. Okay. So I get Q3 here. Q3 here. And here what is this? This is JK, and I will give 1 to this, one high input I am giving. So here everywhere I am giving JK at high input. Here also I am giving high input. Okay. Okay. So this is JK, this is Q1, this is Q0, this is Q2, and this is Q3. This is our J and this is K, J and K. Okay. So this is our normal 0 to 15 counter. Okay, mode 16 counter. Now see here, after 12, after 1100, suddenly when it goes to 1101, what I have to do? After 12, again it has to go to 0 and it should start counting from 0. Okay, so whenever it reaches 1101, 1101, this is nothing but this is Q2, this is Q3, this is Q1, sorry, this is Q3, this is Q2, this is Q1, and this is Q0. Okay, so whenever it reaches 1101, it should go back to 0, or I have to change all the outputs to 0. Okay, that is what I want to do. So for that, for every flip-flop, we are having another pin called clear. Clear. And this is also known as reset pin. Reset pin. So what this clear input will do? Clear input is an active low input. This is an active low input. So whenever we are giving a 0 to this particular pin, all the outputs will get cleared and it will reset to 0. That is what this clear pin will do. So for every flip-flop we are having a pin called clear pin. This is the clear pin. This is an active low pin. That is why I have shown a bubble here. So this is an active low pin. So this active low pin will, if you are giving a 0 value here, if you are giving 0 here, since it is an active low signal, what it will do, irrespective of the inputs J and K and the clock, the outputs will reset. It will reset the output, or all the outputs will go to low. That is what this clear will do. So how we can use this clear input for this particular purpose? Okay, so what we are going to do is, I hope you understood this. What is this clear pin is? So clear pin is an active low pin, and whenever we are giving a 0 value to this particular pin, all the outputs will get cleared, or all the outputs will go to 0, irrespective of the inputs, irrespective of the clock value and J and K inputs, all the outputs will go to 0. That is what we want, right? Because after 12, again I have to start from 0. So if it is at 0, it will automatically go follow this counting steps. But after 12, I have to go to 0. Okay. So how we can implement that? I will use this clear pin for that. So after 12, when automatically it will count the next one. So I get 13. 13 is nothing but 1101. Okay. So when 1101 is reached, where you are getting 1101, this is Q0 and this is Q3. So this is 1, 1, 0, 1. This is 1101. You are counting. This is MSB. Okay, this is MSB and this is LSB. So this is 1101. Okay, 1101. So whenever this input comes, Q3, Q2, Q1, Q0 comes, what I will do? I will change, or I will make this output as 0, or I will reset all these flip-flops. I will reset all the flip-flops. So how I can reset these flip-flops? I will take this Q3, okay, then Q2, then Q1, Q1, and this is MSP, and Q0 I will take. Okay, so I am taking Q0, Q1, Q2 and Q3. Then I will connect this to an AND gate. I will connect this to an AND gate. Okay. So how this NAND gate will behave? If all the inputs are 1, it will give an output 0. So in order to make all the inputs are 1, since this Q1 is 0, I will put a NOT gate here, and all this will be connected to this NAND gate. Okay, so here it is 1. So Q2 was 0, because when 1 1 0 1 is there, automatically I have to clear all the flip-flops. That is what I want to do. So when 1 1 0 1 appears, I have to generate a 0. Then that 0 should clear all the flip-flops. Okay, so if I am using an AND gate here, if all the inputs to this NAND gates are 1, automatically I will get a 0 here. Right? So this output I can use to clear all the flip-flops. Okay. I hope this is clear, because I want to count up to 12. So whenever 13 appears in the output, I have to clear all the flip-flops. How this 13 can be represented in bits? If it is MSB and this is LSB, this is 1 1 0 1 is 13, right? So 1 1 0 1 is 13. So whenever I am getting 1 1 0 1, automatically all the flip-flops should get reset. So for resetting all the flip-flops, what I can do? I can give a active low input to this clear signal. Clear thing. Okay. So how we can give active low signal? Whenever 1 1 0 1 is there in the output, I have to take those inputs and put it in a NAND gate, so that NAND gate will give an output 0. So that 0 I can fed to the clear inputs of all the flip-flops. So automatically whenever this output is 0, it will clear all the flip-flops, and this outputs will automatically go to 0. So after 12, when 13 is reached in the output, so that will clear, that will be given in the NAND gate, and the NAND gate will give you this value 0. So that 0 can be given in the clear inputs of all the flip-flops, and automatically all the outputs will get cleared. So that is how we are generating a mode 13 counter. I hope it is clear for you. So now we have seen how we can generate a mod 13 counter. Suppose you want to generate a mod 10 counter. Mod 10 counter is nothing but it will count from 0, it will go up to 9, and again it will come back to 0. Okay, so this is called a mod 10 counter. So this mod 10 counter is also known as BCD counter. BCD counter. So how we can design a BCD counter? So for a BCD counter, you need how many flip-flops? You need 4 flip-flops, because 3 you can count only up to 7. So anyway, you need 4 flip-flops. So after 9, what you have to do? When 10 is reached, automatically all the flip-flops should get cleared. Okay, so what is 10? 10 is nothing but 1 0 1 0. 1 0 1 0 is 10. Okay, so how we can design that circuitry for a BCD counter? BCD counter or mode 10 counter. So assume that this is MSB and this is LSB. Okay, so this is 10 is 1 0 1 0. So this is 1, this is 0, this is 1 and this is 0. So we are getting 1 0 1 0. You have to read from here because this is MSB 1 0 1 0. So this is Q0, this is Q1, this is Q2 and this is Q3. So you are getting 1 0 1 0. So when you are getting 1 0 1 0, what you have to do? What we have to do? We have to connect the inputs to a NAND gate. You have to connect the input to a NAND gate. So what are the inputs of this NAND gate? We are having Q3. Q3 is 1. So no problem. Since Q2 is 0, what I have to do? I have to complement Q2 and I have to give it as an input. Q2. Then next is Q1. Q1 is 1. So directly you can give Q1. Then what about Q0? Q0 is 0. So Q0 is 0 means you have to complement it and give as an input. Okay, so this is the NAND gate. Actually you have to connect this. Here you are having this is Q2 and Q1 you have to connect here and this is Q0. Okay, so in this way you have to connect. And after getting this, so this is 1, this is 0, 1, 0, that is 10. You are getting 10 here. So when you are getting 10, you have to generate a 0 and that 0 should clear all the flip-flops. Then only after 9 you can go to 0 again. So if it is 1, 0, 1, 0, here it becomes 1. Here also it becomes 1. So all the inputs to this NAND gate becomes 1. So automatically this NAND gate will generate a 0 and this 0 you can use for connecting, can be used for connecting or clearing this flip-flops. So all the flip-flops will get cleared after 9. So when 10 is reached, all the flip-flops will get cleared. So in this way you can design a counter that counts up to a particular level. Okay. Now my next aim is if I want to count here our starting is 0 always, right? I want to start from a different value. So what I have to do? I want to start from a different value. So assume that I want to count from 4 to 10. I want to count from 4 to 10. Okay. So I want to count from 4 to 10. So after I have to start from 4, then count up to 10. Again I have to go back to 4. This is what I want to do. Okay. So we will see how we can design a circuitry for this. So an arbitrary starting and an arbitrary ending point. So I want to count from 4 to 10. So what I can do if I want to count from 4 to 10? I want to start from 4 and I want to finish at 10. So after 10, if it is 11, 11 is nothing but 1 0 1 1. I have to change it to 0. So how I can generate it? So after 10, so if it is this is, you can take it as this is Q0. Okay, I am not connecting all those things. I will write like this. Here I can give. suppose this is Q3, this is Q3, this input is Q3, and this is Q2, this is Q1, and this is Q0. Okay, so 4 inputs I am having. So what is my case? This is 1011, 1011, 1011 is, this is 1011. So wherever there is a 0, what I have to do? Wherever there is a 0, I have to complement it. I have to give it as the input. But what happens? What happens if I am giving clear input to all? If I am giving this output to all, what will happen? After 1011 is nothing but 11. Okay, it is 11. So after 11, I am generating is, whenever an 11 count 11 is encountered, I am generating a 0 here. So if I am giving this clock, this has the clock of all the flip-flops, what it will do? After 10 or after 10, whenever it counts 11, automatically all the flip-flops will be cleared. So after 11, automatically it will go to 0, because I am giving this clear inputs to all the pins. But what we have to do, we have to count, we have to start from 4. Okay, so in order to start from 4, this is Q3, this is Q2, this is Q1, and this is Q0. So what all flip-flops should be cleared? Resetted. Only Q3, Q1, Q0 should be resetted, but Q2 should be 1. Right? Q2 should be 1, and the other 3 flip-flops should be cleared. That is what we want. We don't want to clear the second flip-flop, that is Q2. Okay, so from where we are getting Q2, so this one. So this flip-flop, I don't want to set this to 0. Only this one, and this one I want to set to reset to 0. So this clock input I need not have to give here. Only for these 3 flip-flops I can give this clear signal. Why? Because here if I am giving 0, 0, 0, all the outputs will get, all these outputs will get cleared. It will be resetted. But what about this flip-flop? I have to change this output to, what I have to do? For this Q2 I have to change this to 1. So for that, similar to clear input, there is one more input in our flip-flop which is called preset. Okay. So we are having a preset input. So what this preset will do is, preset is also an active low signal. Okay. So this preset will come here. So for every flip-flop I am having a preset pin also. I am having a preset pin. So whenever the preset pin is low, then its output will be 1. Whenever the preset pin is low, since it is an active low signal, whenever this pin is getting a 0 input, it will make the corresponding output as 1. So it becomes so easy for us to design this now, right? So what we can do, I am generating a 0 here. For all these flip-flops, 3 flip-flops, I will clear the input, clear the output, but for the second flip-flop, I will connect to preset pin. I will connect to this will be connected to preset pin. I will not connect this to clear pin. Why? Because if I am connecting this to clear pin, automatically this output will go low. But that is not that we want, because I want Q2 to be 1 for counting from 4. Because this is 0, 1, 0 is 4. So for this Q2 should be 1. I want to make all other flip-flops 0, but only Q2 should be 1. So for, I have to clear all the 3 flip-flops, Q3, Q1 and Q0, but I have to set the value, or I have to preset this to 1. So for that, this 0 input, I will connect to this preset pin. These are the preset pins. So whenever you are giving an active low input to that particular pin, the corresponding output will go high unless without considering whatever input that they are giving, J, K and clock input, irrespective of J, K and clock input, automatically the output will go high. So what we can do is we can connect this preset to output. Whenever this preset is 0, automatically the output of that flip flop becomes 1. So what we can do is this active low pin and connect to this second flip flop Q2, so that the output will becomes 1. So whenever you are getting 1011, I will generate this circuitry, and this circuitry will clear these 3 flip flops and it will reset this particular flip flop. So what happens after 12, when 13 comes, this output, 3 outputs become 0 and this will become 1. So automatically after 12, count starts from 4. This is nothing but 0, 1, 0, 0. This is nothing but 4. Okay, I hope it is clear. And suppose if I want to connect, if I want to count up to 50. 15 is nothing but, or count up to 40. 1, 1, 1, 0. 1, 1, 1, 0. If I want to count up to 14, and I have to start counting from 0, 0, 1, 0. I have to start from 2. I have to start from 2 and I want to count up to 14. Okay, if I want to do like this, what we can do? I have to start counting from 2 and I want to count up to 14. So how the circuitry will change? What will be the change in the circuitry if I want to start counting from 2 and I want to count up to 40. So up to 40 I have to count. So what happens if 15 comes? 1, 1, 1, 1. If it is 1, all inputs are all Q0, Q2, all are 1. So it means that directly you can connect this pin. So automatically this NAND gate will generate 0, and this output can be used to clear 3 flip flops. What are the 3 flip flops you want to clear? This is Q2, this is Q3, this is Q2, this is Q1 and this is Q0. So which all flip flops should be cleared and which all flip flops should be presetted? Which one should be cleared? Q2, Q3, Q0 should be cleared and Q1 should be preset. So Q2, this is Q2, Q3, Q2 and Q0. So this should be connected and this should be connected and this should be connected. So these 3 flip-flops will be clear. So output of these 3 flip-flops will be 0. What about this Q1? Q1 should be 1. So for making Q1 1, what we can do? I can connect this active low pin to the preset input. Not here. I have to connect it to this. So what happens when a 0 signal comes here? Automatically, irrespective of the input J, K and the clock, automatically the output will go high. So what happens in a nutshell? What is 0, 0, 1, 0? It is nothing but 2. So after 14, when 15 is count 15 is reached, automatically it will go to the state 0, 0, 0, 1, 0, which is nothing but 2. So that you can count from 2 to 14. Suppose you want to count from 7 to 14. If I want to count from 7 to 14. If I want to count from 7 to 14. 7 to 14, what I have to do? You want to count from 7 to 14. So whenever 15 is reached, I want to reset some flip-flops. Which all flip-flops I have to reset? This is Q3, this is Q2, this is Q1 and this is Q0. Okay, so if I want to start from 7 again, whenever 0, 1, 1, 1 is reached, I want to count up to 14 only. So when 15 is reached, again I have to start from 7. So what is the difference in the circuitry? Only I need to clear Q3. All other pins should be 1. Right? All other outputs should be 1. Only Q3 should be cleared. So this clear input I can give only here. This is a clear pin. Here I can give this as clear. This is clear and this is also clear. So only which one I need to reset? Only Q3. Q3 I have to clear. This is active low spin. This is clear. And preset you can say it as PST. Okay, this is a PST pin. Preset PST. This is PST. Okay, so only Q3 I have to clear. So all these, only this clear signal will be given to Q3 so that its output will go 0. What about the other three cases? For Q2, Q1 and Q0, I have to preset it. Okay, I have to preset it. For presetting, what we can do? This signal I can give to all the other preset signal. So I can connect here, I can connect here, I can connect here. So what happens if I am giving 0 from here? If I am giving 0 here, it will go high. If I am giving 0 here, it will go high. If I am giving 0 here, it will go high. So what is our data now? It is nothing but 0, 1, 1, 1, which is nothing but 7. So it starts from 7 again, it will count up to 14. When 15 is reached, automatically the circuitry will work. Okay, so this is how we can design a counter that will count from arbitrary starting and ends in an arbitrary ending point. I hope this particular thing is clear for you. So with this, I conclude this asynchronous counting or ripple counters, and I hope the counting, up counting and down counting is clear for you. Okay, so next we will see how we can design a counter that will count both up and down. Up down counter, up down asynchronous or ripple counter. So that we will see in the next.